All right. This morning we are going to see a review of the generation of the differential equations, review of the transformation of those equations into a block diagram, and we're going to take a step further how we actually go and obtain a transfer function for this example. In the screen you have an example of an electrical system, which we were working on last time. And also you have a mechanical system. And what we did is we had the developing of the differential equations and then the production of the block diagram. So what you see on the screen are the steps that we suggested we follow. And in here it says you apply Kirchhoff's law to each loop. The summation of all voltages around the loop should be 0. That step is revealed right here. The summation of all the voltage, the input voltage is equals to the output voltage, the same thing as saying the summation of all voltages is 0. So you could write it in one side of the equation and set it equal to 0. You could write it the way you see it in here. And what we have in here is we have the voltage V, the source, equals the voltage of the resistor, which is here. And then you have the voltage of the capacitor and the voltage of the inductor. So then we are going to say on step number 2, write the constitutive laws for each element and the relationship to the voltages. What that means is that you see for the R element, the voltage drop is I times R. For the C element is 1 over C, the integral of I dt. And for this inductor, the voltage across the inductor is L times di dt. So those are the basic elements in here. And this, if we put these basic equations here, then we develop the differential equations. See, differential equations in terms of the charge in this case. The reason is that if you keep it in terms of the current, the equation has integration and has differentiation, and it's not in the best format for solution. So we say that I is equal to q dt and then replace it into this equation. We come up with the second order differential equation. Okay, so there we go. So this is the second order differential equation as we have it in terms of q here. So that was the development of the differential equation for the circuit. And then from here we could go and develop the block diagram. But what we did last time, as this is a bit of a review, when we have the differential equation from the mechanical system, we would do a free body diagram where we express all the forces, and then we say the summation of forces equals to mass times acceleration, and we obtain a differential equation like this one over here. You see, what is important here is to realize that the two differential equations that you see on the screen are second order differential equations. I am saying that because of what I said a moment ago, that we need to review the concept of a state space form. Well, it turns out that state space form is first order differential equations. But you see this one is not that, because this has a first order differential equation here and a second order differential equation term. If you go to the mechanical system, you have the second order differential equation here, because this term is like this one, see? So what we're doing right now is going from a second order differential equation to a block diagram. But when we review the issue of the state space form, we need to get them in first order differential equations. So that's a topic in itself that needs a little bit more expansion and explanation. But I would like to start simple, with these two simple examples so that we illustrate what the concept is. Now what we did is from here, we had the differential equation, and I told you the best thing to do is to start with the summation point. And in here you have the, let's see, you have the development of the block diagram from the equations for the circuit. So I think it is very helpful if we review this, this block diagram on how it came about. So you see what's happening here is that from this equation, you can see that this is an input in here, and this is the summation of these voltages. But the way we go about producing this block diagram in here is writing the equation in terms of the highest order derivative. So I think the best thing to do is to write it in terms of this derivative. The highest order derivative is this term right here. Let's see if we can perhaps write a little in here. Okay, see this term right there? If we rewrite the differential equation in terms of this, then it makes it easier to generate the block diagram. Other ways, you could write the block diagram in many ways, but in my experience, it's harder to do it that way. So if you take this in terms of this, then everything falls into place. Like you see here, what we can do is, I'm going to steal this little picture in here and do it again for clarity so that everybody is on the same page here. So 1 second, we need to get an image here so that we can do exactly that, okay? And we do that with our little tool that we have in here. So I am going to start with that idea that we take in this equation, we'll develop the block diagram plus the rest of the explanation on the how to do that simulation. Okay, so what we're going to do is we'll say, okay, this is the pasting here. So we're going to start with this. You could say, you can put a title in here if you want. You can say from an equation to a block diagram. Okay, what I'm trying to say to you is this. trying to say is that we write the equation in terms of this term, that in terms of this term. So what I would do is let's move all the other terms to the other side, like let these terms to the other side. All right, so we're going to say that L times d squared q dt squared is equal to v minus r times dq dt minus 1 over c times q. See, when you do that, now we have the opportunity to write the block diagram in terms of that. In other words, this thing here is a summation point. So if you start with that, you go and say, okay, look, this is my summation point, and the first input block that we have is this V. This is of course the input here. You have the result of this is L times d squared q dt squared, and then you have two others. See, you have this one that says that this is r times dq dt, and of course it's with minus sign, and then you have a minus 1 over c times q, like that. You see, this is what it's important right now. The fact that you can get this differential equation, this summation, into this little picture in here, where the result is this one. So this equation here is saying this is the result of this summation, and that's exactly what this picture is doing. I am telling you this because if you have a system that has 2 or 3 equations, the idea is not going to be any different. But if you keep that orientation, that method, you will be able to develop those block diagrams much easier. Very, very, very much so. So in here, the first thing we're going to do is we say, okay, what about if we divide by 1 over L? And then, of course, what is left is d squared q dt squared. And if you integrate once here, you integrate it once. This is the symbol that Simulink uses for integration. We're going to see in a moment where that symbol came from. And if you integrate it again, you're going to get q. And of course, you could use a scoping here like that. There we go. You see, if you have the QDT and you see this R in here, it's basically an invitation for you to say, look, all this happening here on this block diagram is that when you multiply this signal by R, it actually gets completed here. See? This one is by 1 over C. If you go in here and you do exactly that 1 over C, you complete this one here. And you see, in a very simple way, without much of a difficulty, we were able to generate a block diagram. You see, the important thing is how do we transfer this to the block diagram and do the simulation. Okay. Because in a moment we are going to review the idea of the transfer function, I would like to, and we're going to use the transfer function for doing a little simulation about your system. I would like to use this block diagram to put it into Simulink and do the simulation. So that way we also review that process. So how do we do that? Let's just go in here and say look for MATLAB, and then right here. And so we're going to bring Simulink up, and the idea is to transfer this block diagram into the Simulink. And for that purpose, maybe I'll just have the diagram itself in a small window, perhaps a little smaller here. There we go. I'll have it on the side. In other words, this is what I need to transfer to Simulink. So we have MATLAB on the right hand side, which is just beginning now, and we will see that how we transfer this block diagram into the Simulink. So we have to wait for a moment that MATLAB 2015 comes up. Takes a few moments. I think while we wait for that, I will give you some numbers in case you're trying it yourself as I was going along with this, so that we can test it. So let me see, I'll give them to you now. For the voltage, just put 1/2 volt for V. For the resistor, 0.5 ohms. For the inductor, 1 Henry. And for the capacitor, 1 farad. Those are easy numbers. So what we need here is, just in case, Simulink. So we have this. Simulink is a toolbox of MATLAB, so that's why we need to run it this way. It's not an isolated program. In fact, Simulink is a graphics front end that tells MATLAB what to do. So the actual program that is calculating things for you is MATLAB. So everybody got those numbers? 1/2 for V with voltage, and then 0.5 ohms, 1 Henry, and 1 farad. Okay. So what we need to do is we need to create a new model, and so we open by clicking on this icon over there. We click a new working file in here, where we need to put these blocks, the summation points, and all these blocks. and reproduce this. So what I would like to do is, we say commonly used block. I'll just transfer the elements that I need. This is just my style. I think you could do it one at a time and keep building it. But I like to bring all the things that I'm going to need for now, and then accommodate them in the model here. And then we have a summation point, which I haven't seen yet. The scope we do need, and the summation point is right over here. I think that's about it. So let me put this. I like to have this on the picture on the background in there. So as you can see, we could build it from this block diagrams. Move a little farther down like this, and right here put these blocks, see, and then this one over here. Someplace in there. Okay. One thing that is important is to make sure that the signs are correct. You know, because if you have the sign that is not correct, then nothing is going to work. So around this loop, we need to see what the signs are. You know that this is a plus over here, and this is a minus and minus, obviously. So what we have is we need to double click on this and put those signs the way we want it. So we have plus and minus minus. That's the, so in here we have, make it a little bigger here. Okay, so this is the voltage, you know, the first element in there, right there. I'm just gonna put here V, capital V, like that. This one in here, I want you to know that if you click and then you keep the control key and you click the next one, the computer automatically draws the connection. This one right here was 1 over L, right? And then you're gonna put the L in here, like that. In this one, we need to invert the direction, so you do a control I for invert, and you do a control I for this other one also. What happened? Control I. There you go. So this one is connected over here, and obviously also here. This other one is connected here and connected over here. See? See, it's pretty simple how, and very logical how to do this. These two are the ones. This is the R, and the other one is 1 over C. I'm using capitals, so I'm just going to continue doing that. and this other one in here is going to be 1 over C. So this is the block diagram for the circuit, and as it is in Simulink. What we are going to do is to double click here, and then we'll take a look at the results of the simulation right there. What we need to do is at the prompt either create a script file that has these values, or enter it here. Like, let's see, I gave you the value for that V was equal to 1. I also told you that I mistyped B equals to 1. Yeah, the other value was that C is equal to 1. No, C was equal to 1. B is not. B was 0.5, right?
No, B was 1.
No, the voltage input is 1/2. It's equal to 1/2. And then R I think was 0.5. Yeah. And then C was 1, and L was 1. Yeah. Very good. So given those values and this block diagram and this window, now we can come in here and by clicking this go button, perform the simulation. So hopefully everything goes okay, and it runs, and in fact it did. See here you can see a simulation, but if you put it like this, then you can see it very clearly. Okay, so that is from beginning to end, from the circuit, getting the equations, to the block diagram and getting the simulation done. Okay, now on to the concept of the transfer function, which I would like to review next.